all of you, welcome to my channel. This is Dinesh, chemistry class. So our today topic is the important topic hybridization from chemical bonding. So before knowing the hybridization, we should know the concept on valence shell orbital overlapping. That you have studied in that we call is VBT, valence bond theory. So in valence bond theory explains the formation of various molecules, but valence bond theory fails to explain how the geometry and shapes of various molecules, like why BeCl2 is linear, and BF3 is planar, methane is tetrahedral, ammonia is pyramidal, water is V or angular or bend shape. So why these molecules shows different kind of geometry and shape? So these things cannot be explained by VBT. That's why VBT got failed. So the new concept and a hypothetical theoretical concept, that is called hybridization, which was introduced. So according to that, hybridization. So first of all, let's look the definition of hybridization. Hybrid, we know hybrid. The meaning of hybrid is a new variety. So hybrid orbitals. So whenever there is atomic orbitals is mixing together to form new orbitals, that is called hybrid orbitals. We call it as molecular orbitals also. So according to the definition from NCERT, intermixing of the atomic orbitals of slightly different energies in the formation of new set of molecular orbitals of equivalent energy, shape and size. So in simple, we can understand atomic orbital plus atomic orbital will give molecular orbital. So the energy of each atomic orbitals should be slightly different. So then only we can get the molecular orbital with equivalent energy, shape and size. So here let's look at the question. So let's take this is E1, energy 1, this is energy 2. From this, the correct energy relation of atomic orbitals which leads to hybridization. Yes. So the options are E1 is equal to E2. E1 is greater than E2 and E1 is lesser than E2. Finally, E1 is approximately E2. So now you can guess the correct answer. So we said, as per the definition, atomic orbitals of slightly different energies can form a molecular orbital. So according to that, first option, we have equal energy, so it should not be equal, and which means E1 is greater. Here we said slightly different. In second option we have E1 is greater than E2, but it doesn't mean that how much different is there. Greater means in the sense how much greater we don't know. So but in fourth option, approximately same, the option is given as approximately same, which means the correct information about the definition. So the correct answer is fourth option, because we use the word slightly different. The energy should not be more different. Difference should be very, very less. So according to that point, last option is correct. So let's go to the next question. The orbitals are used in the bond formation. Yes. Atomic orbital, pure orbital, hybrid orbital, valence shell orbital. So before bonding, atomic orbitals are combined to make a molecular orbitals. So that new molecular orbital is also called hybrid orbital. It is a new variety. So according to that orbitals is used in the bond formation. So according to that, third option is correct. So let's go to the next question. One 2s and 3 2p orbitals of carbon hybridize to form new sp3 hybrid orbitals. So the number 1 2s orbital and 3 2p orbital are going to intermix, so that we are going to get how many new sp3 hybrid orbitals. So 1 2 3 4. So generally the number of orbitals which is involving in hybridization, that is called 1 s orbital, will combine with 1 p orbital to produce 2 sp orbitals. So the number of atomic orbitals involved is equal to the number of hybrid orbitals. So it should be equal. Number of atomic orbitals involved is equal to number of molecular orbitals. So in that point, 1s orbital, they said in the question 1 2s and 3 2p. So totally we have 4 sp3 hybrid orbitals will get. So the correct answer is fourth one, 4. So in detail, let's go to the carbon atom. Atomic number 6. The configuration is 1s2, 2s2 and 2p2. So this is the ground state configuration of carbon atom. So I'm picking the valence shell configuration, that is called 2s2 and 2p2. So at excited state, the electron will be moving from s orbital to p orbital to make the valency 4, because number of valence electron is equal to number of bonds. So now we have 4 unpaired electrons, which makes the carbon valency 4. So now this is a s orbital, and each orbital of p we used to mention like px, py and pz. So these 4 orbitals are intermixed together, so that s plus px plus py plus pz, so that we get sp3. So totally here the number of orbitals involved is 4, 1 s orbital and 3 p orbital. So totally we'll get 4 sp3 hybridized orbital. So it should be equal. So based on that you might get a questions. So now whenever there is a p orbital, we used to say px. So this is called lobes which are concentrated on particular axis, that is called x-axis. In py it is concentrated on y-axis. In pz it is concentrated on z-axis. So when this is a pure orbital, if you see a pure orbital of p orbital, that is unhybridized, when it's undergo hybridization, it will be converted into like this. This is pure unhybridized p orbital. The shape of p orbital is dumbbell shape. We used to say dumbbell shape. So that you might have studied in the shapes of orbitals. Okay. Now pure unhybridized orbital, on hybridization it will be giving like this. Okay. So this is the structure of hybridized orbital. So the lobes will be unsymmetrically arranged in the form like this. So this makes more directional, and then it forms a bond easily. So now one s orbital is a spherical shape. So totally all this combines to give 4 equivalent sp3 orbitals. These are the 4 equivalent sp3 orbitals. When hydrogen comes, we have 4 electrons here in the valence shell of carbon atom during excitation. So that if 4 hydrogen atom comes, hydrogen atom is configuration is 1s1, so that but here the hydrogen atom does not involve in hybridization. That will be discussed in later. So now this is the structure of methane, CH4. So this is how it forms. So whenever the hybridization involves between pure hybridized unhybridized p orbital, the shape you should remember, one side it will be elongated and the other side will be very short. So there will be a questions based on that. So let's look the question. Incorrect statement. So the first option is hybridization is a mixing of valence shell electrons. Second option, full-filled, half-filled and vacant orbitals may take part in hybridization. Third option, number of hybrid molecular orbitals is equal to the number of pure atomic orbitals get hybridized. And fourth option is each hybrid molecular orbital having two lobes. One is larger and other is smaller. So as we discussed earlier, so let's look the first option. Hybridization is a mixing of valence shell electron, which means hybridization is nothing but intermixing of atomic orbitals to produce a molecular orbital. So it is a mixing of orbitals, not a valence shell electrons. So based on that, first option is correct, which is incorrect. So let's look the second option, full-filled, half-filled and vacant orbital may take part in hybridization. So there is no condition for orbitals to behave in a such manner to involve in hybridization. It doesn't matter. So full-filled, half-filled and vacant orbitals, all types of orbitals can take part in hybridization. And third option, just now we discussed before, number of hybrid molecular orbitals is equal to the number of pure atomic orbitals that we get hybridized. So that is also correct. And fourth option, each molecular orbital have two lobes, as I discussed before. One should be larger or elongated and other should be smaller. So the three options are correct. The one is incorrect, the first option. Let's go to the next question. So here I make all the questions should cover all the concept. So correct statement regarding. First option. Hybridized orbitals are always equivalent in energy, shape and size. Second option, hybrid orbitals are directed in space in some preferred direction to have minimum repulsion. Between electron pairs and thus a stable arrangement is obtained. Therefore, the type of hybridization indicates the geometry of the molecule. Third option is orbitals present in the valence shell of the atom or involved in hybridization and promotion of electron is not an essential condition prior to hybridization. So the fourth one, all are correct. So let's look the first option. Hybridized orbital are always equivalent in energy, shape and size. Yes, that is correct. In second option, hybrid orbitals are directed in space in some preferred direction to have a minimum repulsion between electron pairs. So orbitals should be placed in a minimum repulsion so that it makes a perfect geometry. So according to that, because all are electron pairs, those electron pairs may repel each other. That's the repulsion between the lone pair, bond pair, bond pair, bond pair, everything you might have studied in VSEPR theory, that is called valence shell electron pair repulsion theory. So based on that, it should have a minimum repulsion so that it make a perfect geometry. So that is also correct. And third option, orbitals present in the valence shell of the atom are involved in hybridization, that is correct. And promotion of electron is not an essential condition. In terms of methane, we have discussed that the electron will be promoted from 2s to 2p. So that's not the prior condition to undergo hybridization. So without promotion also the hybridization can happen. So in point of all these concepts, so all are correct. So I have covered all the important points in terms of questions, so that if you revise all these questions, you no need to study the concept. Okay, so in that way I have prepared this question. So now let's go for the determination of hybridization, how to find out hybridization. So we have two methods. To determine the hybridization.